Hello and welcome to Paracetamour Academy. We are your tutors for medicinal chemistry. You know where to click whenever you have trouble with any given chapter. It's a pleasure for us to be presenting this series of tutoring videos in hopes of enhancing your knowledge and improving your understanding of the materials. My name is Marc Anlian. I'm a fourth-year pharmacy student at the Lebanese American University and a tutor for Paracetamour Academy. And now we're going to be covering local anesthetics, part 2. For the outline of this presentation, we're going to go over a review of the structure-activity relationship of the local anesthetics, as well as considerations in design. The SAR of local anesthetics contains a lipophilic portion, an intermediate chain, and a hydrophilic part. And we're going to tackle these separately. Before getting into the three parts component of the local anesthetics, we're going to go over a key concept here, that the stability of the local anesthetic is a key factor that affects its duration of action. As you can see, all four of the agents on this table are esters. This is going to have an effect on the duration of action by actually decreasing it compared to amide type of local anesthetics, and the reason behind that is that esters tend to be rapidly hydrolyzed. This is not the case for tetracaine, but we're going to tackle tetracaine separately, and its duration of action is exceptionally long in that category of local anesthetics. In comparison, the amide type local anesthetics, as we can see them, tend to have better duration of action compared to the esters because they are more resistant to hydrolysis. This, in fact, is related to the intermediate chain part of the three-part structure. The three major components of a local anesthetic include its lipophilic portion, its intermediate chain, as well as its hydrophilic part. The lipophilic portion, which is here on the left side of the graph, is usually a phenyl ring. It is essential for activity, and it is involved in the formation of a Zwitter-ion, which we're going to tackle a couple of slides ahead. And it usually has a substitution for an electron donating group, such as the ones I'm underlining. A methyl or an amino group is going to donate an electron into the ring structure, and consequently, for these drugs, the electron donating group being in ortho or para position is usually better than to be in meta position. In fact, for all of these agents, none of them is in meta position. And the reason behind that is that an ortho or a para position is going to contribute to creating a double bond conjugation. As you can see, we have here single alternating with double, then single alternating with double, single, and then you can consider that there are the free electrons which alternates back and then double. And this form of alternation between the single and the double bonds is going to enhance the stability of your compound. It would not be possible if your substitution was in the meta position, because then there is no more alternation. We have a single with a double bond, but it's not quite the same as what happens with an ortho or a para position. Concerning the intermediate chain, it determines the stability of your local anesthetic. And finally, the hydrophilic part, which is at the rightmost of the scheme, is not necessary to activity, or rather, its necessity is controversial, and it has miscellaneous effects on the SAR. We're going to cover them. If we zoom into the lipophilic portion and we decide to compare a couple of agents, we can see that, for example, procaine's lipophilic portion consists of the phenyl ring with the NH2 substituted in the para position, right here. Now, if we take the structure of procaine, it was found that inserting a methylene group between the phenyl ring, which is here, and the carbonyl group there, the carbonyl group of the ester, so this methylene right here, is actually going to provide support in the formation of Zwitter ions. We're going to tackle why Zwitter ions are so important. And now if we look at one of the newer agents, tetracaine, it is believed to be between 6 to 50 times more potent than procaine. And this is because of the N-butyl substitution being superior. Again, so this is your substitution. This is the lipophilic portion. This is going to represent the intermediate chain. And finally, to the rightmost, we have the hydrophilic part of the local anesthetics. I insisted to align the phenyl rings in order to help you visualize what's going on with your local anesthetic. Now to zoom back into the N-butyl substitution right here, what is happening is that it is going to increase the lipophilicity of your compound because you are adding more carbons. And it is also going to increase the formation of a Zwitter-ion. And this is why it's believed that tetracaine is that much more potent than, for example, procaine. But then, what's the deal with the Zwitter-ion? Why is it so important that we're creating a Zwitter-ion structure? These are the schemes that show us how procaine on the left, representative of the esters, and on the right we have lidocaine, representative of the amide type local anesthetics. This is how they undergo this Zwitter-ion formation. For lidocaine, the process is different because you can visualize it in a form or another. Lidocaine is not going to change structure, but what's happening instead is that in its unionized form, it can go into the Zwitter ionic form, thanks to the way that the electrons on the N atom can eventually conjugate with the carbonyl group. This is what's happening at that level. And here the scheme illustrates pretty nicely what happens with the single double bond conjugation, and you can visualize that if this group was in meta position, the same conjugation would not be possible, because the double bond then would be completely adjacent to the double bond here, and therefore all it would do is stabilize the ring itself and not the rest of the molecule. The intermediate chain of local anesthetics, I want you to remember two key concepts from here. That the type of the portion is going to affect the resistance to hydrolysis and the duration of action. And as we've mentioned, the esters are more prone to rapid hydrolysis, whereas the amides are more resistant. This is an amide. It's going to be harder for esterase to break down the amide due to the presence of the NH group here. The second thing I want you to remember is that having a longer chain, so if we went beyond having 2 to 3 carbons, would actually increase the pKa. And a higher pKa means that we're resulting in less absorption of the local anesthetic, because more of the unionized form is not going to be able to, or rather more of the ionized form is going to remain outside, and therefore not going to be able to cross the skin and become unionized. So less of the unionized form, which is the active form, is going to be available for use. Now concerning the hydrophilic part, most local anesthetics contain an aminoalkyl group, which is either tertiary or secondary. Some do not contain it, and yet they remain potent anesthetic agents, so the necessity is controversial. Now, secondary amines are more active, but they may cause more local irritation when you apply the anesthetic. Primary amines, we don't talk much about them because they have weaker activity, and they are also associated with irritation, leaving us in the worst of both worlds. Now I'm going to talk about considerations in drug design and what the Zwitter-ion formation is useful for is that it's going to maximize penetration of the local anesthetic into the nerve membrane while also helping minimizing losses to circulation. Because the Zwitter-ion, if I go back a couple of slides, is simultaneously positive and negative, or rather simultaneously charged and uncharged. And this is, in a way or another, the major property that it has in order to help us achieve this point. Another thing is that local anesthetics are mainly available as racemic mixtures. The presence of adipose tissue will also decrease the local anesthetic activity due to the distribution of the drug, and a limitation of blood flow into the site of injection will increase the duration of action due to decreasing the systemic uptake of the local anesthetic. And whenever we can achieve that, we're reducing the toxicity of this drug. Now, because we're talking about local anesthetics, at therapeutic doses, they're very rarely going to be toxic whatsoever. Other considerations to think about in drug design would be metabolism and drug-drug interactions. For metabolism, if we take the example of procaine, it is going to be hydrolyzed into these two separate compounds. And in terms of drug-drug interactions, we have two notable ones. First, with acetylcholinesterase enzyme inhibitors, because they compete for the same enzyme. And then benzocaine especially seems to have a drug-drug interaction with sulfonamide antibiotics, because if you look at the two structures, this is benzocaine and this is sulfonamide antibiotics. They share some similarity in the structure, by which it is believed that they can lead to hypersensitivity reactions if there's cross-resistance to one to another. But this pens having more trials about it to really understand what's going on. So the drugs are relatively safe. They don't have an extensive list of drug-drug interactions. You're using local anesthetics to create a topical effect. So it is not expected of those agents to have a huge list of drug-drug interactions. To continue with the concept of metabolism, if we take lidocaine, its various pathways of metabolism include N-dealkylation by CYP1A2, which can lead to two metabolites that have CNS toxicities, monoethyl glycine xylidide and glycine xylidide. The solution for that would be to create lidocaine analogs that have ways or another to avoid this metabolism. Tokainide is such an agent that is not metabolized into any of the two CNS toxic metabolites of lidocaine. Tolikaine does it differently because it is hydrolyzed to give a carboxylate ion, which will become ionized and will not be able to cross the CNS, leading to no toxicity either. So those lidocaine analogs are a form of consideration of drug design in the way that they avoid the metabolism by which lidocaine produces CNS toxicity. This is a wrap for this chapter. Local anesthetics have three major parts, which include their lipophilic, their intermediate chain, and their hydrophilic portions. And you have to keep that to mind whenever you're studying this chapter to know how to compare between the different agents. And you have to keep to mind the extent to which metabolism plays a role, whether it is the hydrolysis of your ester moiety or whether it is the formation of toxic metabolites. And every consideration we have discussed goes into the drug design of those agents. So thank you for watching and stay tuned for more. Please like and subscribe. Let us grow this channel together. Brought to you by Paracetamour Academy.